Okay, so this is problem 419. We just talked in class a little bit about how to find the equations in the first 4 feet. Again, if you cut it, the left-hand side looks to be the clear choice. And if you go over here from 10 to 14 and cut it, it looks like the right side. So we're going to today we're going to look at what happens here in the middle. So again, this is probably what we're going to choose, something that looks like that. So in order to accomplish that, and this equation will only be good from 4 to 10, this middle section, we're going to need the reaction at A. So with that as our strategy, let's go ahead and do that. So I'm going to draw my free body diagram for this. So I have my 250-pound force on each of the cantilever ends. And then here in the middle section, I have my distributed force of 150 pounds per foot. And these dimensions are 4, 6, and 4. Now at my support condition, at A is a roller, so I'll assume that I have a reaction up. And B is a pin, so I would have a BY and a BX. I'm going to take my distributed load and resolve that into a concentrated equivalent. What's that value? It's always the area under the curve, so that'd be 150 times 6.
900.
900. Now I'm going to I'm going to find the reaction at A, so I'll probably sum moments about B. So what's the distance from that force to B?
3.
Half of 6, 3. So that should be enough to get me started. So let's come in here and sum the moments about point B for the whole free body diagram. I'll just start from the right side and go this way. So look at this 250 force. What kind of moment does it create about B using my sign convention? Looks like it's negative. So I'll have a negative 250. And its moment arm is 4 feet. Then I'll have the 900-pound force, which creates positive moment, 900 pounds. We found its moment arm, that's 3 feet. Then I hit this 250, which creates positive moment. And let's see, that's 6 plus 4, that's 10. And then finally my reaction AY. And the way I've assumed it here, what kind of moment does it create about B? Negative. So that's BY, and its moment arm is...
You mean AY?
Oh, sorry. AY. Its moment arm is 6 feet. So I should be able to find AY. I'm guessing it's going to be 700.
Yeah. Can you do symmetry on that one?
Yeah. You should expect it. I mean, the geometry is symmetric, the loading is symmetric, so if you add everything up, 500 plus 900 is 1400, half should go to each. So what is that, 700? And I got the right, I didn't get the right, I got positive, so it is up. So now when I'm ready to do my free body diagram for the section between A and B, this section, cutting it right here, let's draw that. So again, I'll give my beam some depth. I'll have my reaction, which we just found, 700 pounds. I have the applied load at the left edge, 250. And then I have a partial distributed load. And I know the intensity of that load is still 150 pounds, right? And then at the cut, the actual cut I'm making, I've got my positive shear force and positive bending moment. Now let's get some dimensions. This overhang section is 4 feet. Remember, I'm measuring X like this. So this dimension in here will be X minus 4. Everybody see that? So I think my free body diagram is in pretty good shape. So I'll take my force here and create a concentrated equivalent. I'll just call that F. And then from the cut surface, it'll have a distance D away. So what's F? Just the area of the triangle, of the rectangle, base times height. So the height is 150, and the base is X minus 4. And the distance, half. So I'll get X minus 4 over 2. That should be all I need. Now I just process my equations. So I'll just start this one here. So I'll sum moments about the cut, set them equal to 0. So starting here, this moment, my internal moment, is creating, with my sign convention, positive moment. What about the force, the equivalent force, positive or negative?
Negative.
Positive.
Okay, you said both. Should we vote?
Positive.
Everybody vote. Say aye if it's positive.
Positive.
All opposed? Oh, good. So it's positive. So what is F? F is 150 times X minus 4. That's a 4, by the way. Sorry about that. And it has a moment arm of... I'm just going to tuck the 1/2 out on the side. We'll take care of that later. So just to make sure you see that, this part is the force and this part is the distance. Then I have my 700-pound force. What kind of moment does it create?
Negative.
Negative. So negative 700, and what's its moment arm? X minus 4. Then all the way out to the end, this 250 creates positive moment and has a moment arm of X. So now we'll just collect all the terms. So our moment as a function of X is equal to... Now look at this first chunk here. The half will get the 150 and I'll get 75, and that'll be X minus 4 squared. I can do a little tidying up here. I've got negative 700 times X plus 250 times X, right? So when I throw that to the other side of the equation, I get a positive 450, right? And then I'm left with the negative 700 times 4, which is 2800. That's positive. When I throw it to the other side, it should be negative. And all of those should have the units of pound feet. So let's make sure I did that right. So 75, that's right. And that went to the other side of the equation, so I got a negative. And then I get a positive 450. Yeah, that looks okay to me. We can check it in a second. Now remember, this equation, and I forgot to write this down, this is only good from 4 to 10. Right? Just in this region. And really I don't have anything to check it with because I don't know any moments in that region just by looking at it. I know I got moments and shears here on these free ends, but that's not going to help me. So if you really wanted to check this, you would have to compare this moment equation at, say, x equal 4 with the equation from the first section at x equal 4 and hope the moments matched. And since we're not working that part of the problem, we can't make that check.
And then I have a question about the less than and equal to. I wrote the same thing you did, but in the back of the book, it has just less than both of them.
It won't matter.
Oh,
I mean, the equation is still good at 4.
okay. So it does include 4?
Oh, yeah. Well, you can see what happens when x is equal to 4. That term drops out. But you still have this. That should give you the same moment at x equal 4 from the first equation, or set of equations. But we didn't write those. I guess just to finish the problem, kind of running out of space, I'll kind of slide it over here. We'll go ahead and sum forces in the y direction. Set that equilibrium. That would help us find the shear. So in this case, shear is acting down. Our force is down, which is 150 x minus 4. We have 700 up, and then we have 250 acting down. So I'll write it over here. So our shear force equation is going to be all this stuff. So I can do a little tidying up here. So that'll be negative 150x. And then I've got this, which is positive 600, plus this is 1300, minus 250 is 1050. And that would be positive. Hopefully I did that right.
It is.
And we can check. Let's see if we get the derivative. So what happens here? Oh, it's a mess.
It is right.
Yeah. Are you sure?
Yeah, it's in the back of the book.
Oh, that's in the back. Hey, okay, I'll go with that. Normally I don't necessarily trust the back of the book. It's right more often than it's not, but it can be not. There's a few of them.
That's nice.
So anybody have any questions about that? I'll go ahead and turn that one off. Questions? No?